Today's webinar, avoid PCB manufacturing and product assembly issues via integrated electronic and mechanical CAD. So today I'm joined by our partner from MacroFab, Chris Church. He's the Chief Product Officer. My name is George Garcia. And in this webinar, we're going to be learning quite a few things. So to get started, we're going to give you a brief intro about ourselves, who we are, why you should care what we have to say. We're also going to give you an intro about Autodesk and MacroFab and how the services that we provide can help you get your products to market faster. We're going to be looking at the benefits of DRC and why it's so important to be able to get your board manufactured. We're going to look at how Fusion 360's E-CAD, M-CAD integration, the ability to very quickly have a legitimate 3D model of the PCB, gives you a lot of advantages when it comes time to make manufacturing and assembly decisions. And that's something we're going to see as we go through this. We're going to talk about manufacturing considerations, things to keep in mind for making your final product. It's not just about the PCB. And then finally, how you can get your manufacturing files to your manufacturing partner, whether they be Gerber's, the native Eagle file, or ODB++. So who are we? Let's start with Chris.
Hey, George, thanks for having me today. So a little background on myself, guys. My name is Chris Church. I've spent about, first off, I'm the founder and chief product officer at MacroFab, but I spent about 20 years in software development before moving into robotics. Started a robotics company for making motion control systems for filmmakers. Led that company for several years. We designed a lot of products, worked with a lot of manufacturers, and then over time, I've really felt that we could provide a much better digital-first, software-driven experience around contract manufacturing. So I decided to start MacroFab, and we've been around for about 8 years now, and I've been working with thousands of customers, helping them to produce their products effectively.
Awesome. Thank you, Chris. Definitely, it's going to be a pleasure to enjoy your experience today. So my name is Jorge Garcia. I am a Fusion 360 Eagle Community Manager here at Autodesk. I've been working with Eagle for over 10 years. I was part of the CADsoft acquisition when we came in. I do have my degree in electronics engineering. I love electronics. I love building projects. One of the best things I get to do here at Autodesk is make the demos. So, besides the hardware, I do also enjoy programming. So I do a little bit of that. And that comes into play with some of these projects. So it's not going to be in this one today. We have a lot of hardware today. But, if there's ever a question with that, I may be able to give some assistance there as well. So let's talk about who is Autodesk. It may seem like an obvious thing to think about since you're coming to an Autodesk webinar. But if you think about it, Autodesk makes a lot of products. Last I checked, our catalog is over 100 different products. But you can really easily organize it in these three industries: architecture, engineering, construction, media and entertainment, design and manufacturing. Electronics falls under the design and manufacturing umbrella. But if you work in any of these industries, it's likely that at some point you've worked with our software. Now, who is MacroFab? Chris?
Yeah, so to put it very simply, at MacroFab, we are a digital electronics manufacturing platform. Our customers can come in, upload their design files, get instantaneous feedback on their design, whether it's pricing, sourcing availability, lead time. And then we work with a network of factories across North America, making it easier for our customers to scale up or scale down, whether we're thinking about Mexico or Canada or the US. And we work with our customers at all stages of their product lifecycle, from one-off prototypes to scale up and high volume production. We manage all of this through a digital manufacturing platform with the focus of reducing the supply chain risks and increasing the agility within your organization.
Excellent. So let's talk a little bit now about the tool we're going to be using today, which is Fusion 360. The key is in the name, the word Fusion. Fusion, as you may or may not be aware of, is used for mechanical modeling. It does thermal simulation, it does stress simulation, it does drawing, it does electronics. It's not any one of these things, but rather all of these things put together. And the idea is by bringing all this functionality under one roof, that's going to increase your productivity because you're going to avoid having to do translations between different pieces of software. Everything is in one place, and that helps make you more productive. So at this point, I'm going to switch over to Fusion 360, and we're going to talk through a design. Now, we recommend that you as designers have this conversation with your manufacturing partner. with one of the representatives. In this case, I have the privilege of having it with Chris, but in most cases, there's probably going to be a team of partners that the different manufacturers will have who are going to be able to help you go through this type of analysis. So I'm going to go ahead and share my Fusion design. Bear with me one second. And here we are. So right now we're looking at the electronics design document. Now in Fusion 360, the electronics design document is the central hub. This is what links your schematic, links your board, and links the 3D model of the PCB together. It is through this mechanism that everything is kept in sync. And as you can see in this case, for this simple design, I already have a schematic linked, I have a 2D PCB linked, and I have a 3D PCB model. Now, schematic capture is the same as in any other tool. You put in your symbols, you draw the connections. And then for our purposes, since we're more interested in the manufacturing and in the assembly, we're going to be focusing mainly on the 2D PCB. Although there are going to be a few things we're going to be able to do here on the schematic as well. So starting with the 2D PCB, right now you can see it's a very simple design. It's all analog. And from here, and this is one of the key benefits of Fusion 360, when you have your model set up with 3D, when you have your library set up with 3D models, from 2D PCB to 3D PCB is just this click. Literally, that's all it takes to get an exact 3D model of your PCB. And as we go through this conversation with Chris, we're going to see just how useful it is to have a nice 3D model of the PCB. It's not a rendering. It's not just a picture. This is a 3D model that we can rotate, we can analyze. So Chris, let me know. Let's go ahead and get started. If there's anything that calls out to you, anything you want to check out first, whether it be here in the 2D PCB.
Well, let's go to the 2D PCB and let's talk about design rules. So thinking, from the perspective of design rules, every manufacturer out there, when we're talking about the PCB and even into the mechanical assembly part of it, they're going to have some number of design rules for you. Typically, those will be posted on their website. But with MacroFab, we actually give you the design rule files for Fusion 360 ready to go. I'll actually post a link right here in the chat in GitHub. And then you can just load these design rules for your design, and it will tell you where you're within certain price points or making an unmanufacturable design. It can give you that feedback instantaneously. And this is something we ask everyone start with. And at MacroFab, we try to make that as easy as possible by giving you the rule files. You don't have to read a web page and type in all the values. Our focus is really making your life as easy as possible.
Awesome. So that's something that to keep in mind. That's a benefit that users will obtain by going to MacroFab, because you just give them the file. If you're dealing with a manufacturer who doesn't have a DRU file already made, then you have to look up their specifications on their website, interpret them, and then fill out the corresponding fields here in the DRC.
Yeah,
to make sure.
George, yeah. While we're here, someone's asked a question about whether Eagle and Fusion 360 are fully merged now, and are there any, is there any drawback to just using Fusion 360 over Eagle from a design perspective?
So from a design perspective, they're almost fully merged, almost. Literally, there's one major feature missing, which is design blocks, but that's actually coming in soon. That's being worked on as we speak. So once that's in, at that point, I would argue that there's little to no benefit to just be using Eagle, because here, you have all the functionality that Eagle's providing, plus everything else that Fusion brings with you. So whoever asked that question, thank you for taking the time to put in the question. And again, feel free, anyone, to put in something in the Q&A, and we'll be happy to address it.
Now, George, one thing I really love about Fusion 360, and I know our team likes a lot, is the ability for us to work together in the 3D design view. Because, getting the design files, with MacroFab, we try to make it as easy as possible to build the design you're looking for. You can upload your Eagle files, you can upload your ODB++, But there's something, really magical that happens when we're looking at that 3D version that our MPI team, because we work with a lot of customers, not just on building their PCBs, but really building the final product, and having that 3D view for our engineering team to be able to walk through with you, that's really great. I mean, and I think that's something I'd love to do here, is kind of talk about that and work through like our engineering team would, with our customers, to kind of talk about some of the challenges we may see and some things that we can do that this 3D view enables us to do.
Excellent. So I've pulled it up. Let's go ahead and take a look. Let me know if there's anything you see.
Great. So one of the things I'm looking at here is this particular transformer. Now, one of the notes, can we tilt up a little bit? For some reason, there we go. I'm noticing there's a gap there, right? Is that gap physically important to your design?
Not in this one. In this design, it's not physically critical, no.
Okay, because with a lot of components, and this is something we see a lot with our customers, is there's a very specific need, especially when we're thinking about the 3D world, there's a very specific need for why a component is in a position it's in. So if this transformer were, for example, interacting with something in the enclosure, which, I think later we're going to get the chance to see the enclosure and all of that and talk about that. But if it were interacting with something there and we needed to set that position very, very specifically, we would want to create some kind of tooling or shim, or take, a lead forming example, strategy to prevent, variation in that. So in this particular case, it is not important in its height location, but if it were, you could design that shim here in 360 so that we could actually go 3D print that, or produce it in whatever way we need. I mean, of course, our team can design it for you also, right? But working together in Fusion 360, we could visually see that that shim is going to fit. It's going to give us the height we want, etc. But let's go ahead and rotate. I want to look at these guys here, these heat sinks. For some reason, yeah, there we go. Okay, so my first question for you is, how are those heat sinks? And this is something we see a lot of, and heat sinks are very common, especially in high power applications. We see a lot of this, and we do work with a lot of customers that have heat sinks in their designs, and we have this kind of conversation with them. So my first question is really going to be, how are those physically attached to your board?
So as designed right now, I have them so when I bought these heat sinks, they actually have these little nubs, and those little nubs solder into the PCB.
Okay.
So if you look, they have some thermal relief.
Right.
They're set up to solder to ground.
While they do have thermal relief on the pad, let's remember these are heat sinks, right? And their job is to transmit heat away. So while it is perfectly possible for us to solder those, it does create some challenges in the amount of heat we have to apply to get those up to the temperature they're going to need to be. And this is, again, this is the sort of expertise when you've done a few of these, a few thousand of these, right? You start to see these kind of patterns. So, what we see as a more successful strategy is we can apply solder there for additional, support. But typically, if we look at these heat sinks, they're going to have a hole in them, and those holes are going to be threaded. And we'll see that right here, for example, there's that threaded hole. We're going to use those because they're threaded. They enable us, they line up with that hole in that TO220, and that's going to enable us to put a screw in there. And when we think about from the manufacturing perspective, we still need to transfer heat from that TO220 to the heat sink. So you're going to need some sort of heat transfer paste, like the same as you would see in like the CPU on your computer between the fan and the CPU. We're going to need some kind of heat transfer paste because we can't rely on just that physical connection. And this is something that's not going to show up in your E-BOM in a lot of cases, right? This is a consumable, but we need to talk that through, what the process is. We can use heat tape, etc. But if you could give me the top view, I want to see something here as well, because I see something that's concerning me and that our engineers would be concerned with as well. What's the distance between these two devices here?
So let's use the inspect command in Fusion 360. We can check this surface to this surface right here. It's about 46 millimeters right now, Chris.
Okay, that's not really a lot of space. And if we think about how, as a physical process, we'd have to assemble those, where we're going to be ending up with is we're going to have to get a screwdriver in for that bottom one, right? Because it's going to go through that TO220 into that threaded hole. By measuring this, we can see that I can't actually fit a screwdriver between those two things. So I'm going to be bumping against that other TO220 or screwing in at an angle. It's going to be very challenging. So this is something, by looking together at this design and thinking about the manufacturing process, we can look at that and say, for a more repeatable build, we want to turn that bottom, the heat one, around so that the screw is coming in from the outside, so that we can use a very standard process of just come in with a screwdriver and attach those. It's going to be lower cost, it's going to be faster, it's going to be more reliable and less likely to damage that board.
Excellent. So let me do this then. Since we're on that subject, using Fusion 360, it's very easy to move a component. So what I'll do is I'll click move, I'll select it, and I'll go ahead and rotate it. I'll make sure it's rotated over here. And one thing that's very cool is that we have this option to update the 2D PCB and reroute it. So what I want to do is I'm going to go ahead and try to place it more or less in the correct location. And then I'll rotate it. So that way we can get it how we want it to be. So ZXY. Oh, I almost had it perfect. But okay, but the idea is sound. And if you look on the 2D PCB from making that change, you'll notice that it actually tries to reroute it. So to give you something sensible. And this is something that's unique to Fusion 360. So I could actually right here just finish the move, finish making the rotation, and then have it reroute again. But I think the concept is demonstrated. You know, you have something here, you can just fix it, and then it will automatically try to reroute everything on the 2D PCB. So to keep everything in sync and keep everything in a reasonable state.
Right, and absolutely. And when we're working together with our engineering team and with you guys, what we can do is, right as soon as you make that change, we can upload that design, re-upload it. It'll pick up just that change and enable us to push that. We could have an order in production, and we can go ahead and snapshot that and make an engineering change on the fly while we're working and talking together through that. So now, let's look at anything else there on that design. Now I see the LED. I see that you have it there flush. That makes it real easy to produce. What we'll see a lot of times is that the LED, and by this LED, I'm talking about this one right here. When we see these LEDs, a lot of times what we see are an interaction between an LED or some kind of control input and the enclosure itself. For example, you may want it bent at an angle and kind of stepped out and interacting, maybe pushing through the face of the enclosure. When we're doing that, the challenge always becomes with how we actually repeatedly do those bends and do that height placement, et cetera. So just like we would do a shim with the that transformer, if we had needed to, we can do the same thing with the LED, and you can even model that up. One of the very common things out there are to use standoffs with the LEDs. There are a lot of them available if you need to set it at a certain height. You can bring in that model, add it to your EBOM, and then that way we can see it already part of it. When you upload that ODB++ file out of Eagle to us, it'll automatically bring that in. We'll know the position, and it will be very, very clear to the manufacturing side that that's used to set the height of that PCB. And again, that's something we talk about from a repeatability perspective. So I don't see any other major, assembly issues here. So George, how do you intend to test this?
So my original intent was just to basically connect power to it, measure the output voltage, and then turn the voltage adjust potentiometer and make sure that I'm getting the readings that I need to see at the output.
Okay, okay. We see this a lot. We work with a lot of customers, and at MacroFab, a lot of people may not realize this because it's not like right there in every screen when you see it. We do a lot of testing and product validation with our customers. We help develop their test strategies. We help develop their test fixtures. And when I see this device, I think it's worth talking about, what an effective way to test it is and how we can make some design changes that'll help us do that. Because I'm noticing we don't have really any test points. I did have the opportunity to look at this design earlier, so I noticed we don't have any test points anywhere. So thinking about how we would test this device, I'm noticing there's a very small amount of SMT. If this was an SMT heavy board, a lot of digital logic, we would use something like in-circuit test or flying probe. And with the in-circuit test, it's a little less flexible than flying probe because what we would use is a fixture that's kind of set in one design, but that's in line in the SMT process. So we want to make that as easy and as cost effective as to do. So if we had a lot of SMT here, we'd put all our test points on one side preferably. It makes it real easy. We only have to develop one fixture. It's very cost effective. Likewise with flying probe, we can use the actual pins on components like these guys here, but it's often unreliable. So we're still going to want to add some test points for those devices. And someone just asked me, how much does it cost to manufacture that PCB? What I can say is you can upload it to MacroFab and you can find out in just a few minutes. We give real-time pricing straight from your design files. But let's think about this one. As you said earlier, this is primarily an analog device. You want to test it by feeding power in and reading the voltage off the outside on the right side there and adjust that potentiometer. So the first thing, what we would do there, how we would typically approach that is we would create what's called a test fixture. Because we are dealing with AC on the left side of that circuit board, it could be very, very dangerous. And we want to protect that operator from it. So we're going to be creating an enclosed fixture. And plugging in wires and screwing them, adds a lot of money and cost. You don't really want to pay someone to screw those in. So on the bottom, one of the questions about that just came in right now is, and this is very, very relevant here, what size test points do we recommend? So typically for SMT, the minimum size we're going to want to deal with are going to be 100 mils, 100 thousandths of an inch. That is very, very small. I would typically prefer them to be 2 or 3 times that size if possible, but we can fit a lot in there as long as they're minimum size of 100 mil and have 100 mil spacing. We can go smaller than that, but the costs go up quite a bit. On this AC side, again, I don't know how much current this thing's going to be running through, but our engineers will size those test points with you to make sure we can put the appropriate amount of power through an analog, power circuit like this. So they'll probably be larger on that AC side and slightly smaller on the DC side, just to make sure that we have enough there. But so here we're going to want to add test points because having someone plug in those wires is going to add a lot of cost. We need to protect the operator from that. So we would design this test fixture for you, and we'd ask to add test points on the left side for the AC input and test points on the right side, both for the DC outputs and that V-adjust potentiometer. Because we're going to want to test a couple of things, right? One is that as we make changes, that potentiometer, that the DC levels change the way we're expecting, but we may want to test also that potentiometer is within spec. And thinking about from your hardware design here as well, we would use hollow D shafts. So we'll design that test fixture for you, but we would just, use a D shaft coming down from outside of that fixture to allow the modification of that and then doing the readouts on it. So this is something we work with you very closely, given your cost perspective, given the the volumes you're trying to produce, and develop the right test strategy. But this is going into enclosure, right, George? We're going to be building a final device for you.
That's right. I'm going to be showing you that one in a second. Let me just to show our users here who have joined. If you did want to add test points are a library item like anything else. You would go to the add command, and then in the add command, you can search for test and it'll show up. So we can go over here. I'll do a little search real quick.
So while you're doing that, I'm going to answer a couple questions. One of them that came in is, at what quantities does the test fixture and final assembly become cost effective? It is going to depend on the design. If we're talking about a very expensive E-bomb, a very expensive design for the PCB assembly, adding a minute or two of labor for the testing may not be a big deal. But typical labor rates, if we're thinking US, run around $1 a minute at different factories. So for every minute of test, you're adding $1 to the device cost. So if we can work with you and build a test fixture for $15,000, does it save 15,000 minutes over the course of your production? That's really what we're going to be looking at there, is kind of the life cycle of the product, how much time we're saving, et cetera. The other question there, would MacroFab suggest design improvements, dimensional increases to pads and anti-pads to reduce drill effects of drill wander? We can. Typically, our design rules, keep you within spec of that drill wander we're looking for. So if we talk about, I think in our previous webinar, we talked about annular rings and a lot of the rules around those. And you guys can go reference that one. We have a lot of detail in there as well. I believe it's available online. But we try to keep you within the spec that keeps it within tolerance. If you're on the, that edge of tolerance, that's where we'll start looking at different strategies there. And yes, our design for manufacturability, or, design for test team will help you develop the right strategies there.
Excellent. So I just went real quick to show it in the add command. Here's a test point, and we can put it on the bottom, which in this case probably be the best spot. I have lots of room, so it's obviously we can work that out. In the final fully cooked version, you'll see all the test points populated and everything. Mm-hmm. So let's go to the enclosure now. Okay, so we have the design, and now we have an enclosure that's been modeled in Fusion. So not only can you do the electronics, you can do your enclosure design here as well. So let me go ahead and just show you this one, give you kind of a bird's eye view of how it's set up. This one has a fan. The fan is a separate model. Manufacturer was very generous in how well they made that model. And then I have a connector for the fan right here. So
yeah, and this is great because we deal quite often with customers that have enclosures, and we're doing the final assembly, whether it's programming, testing, putting in the enclosure. We do handle sourcing all of those materials for our customers. And a lot of times what we'll get are disconnected, 2D CAD files, right? PDFs of everything. And you have to really reason about how all that's going to go together, and think about where the design issues and interfaces are going to be. And that can be really challenging. A lot of times what we'll have to do is what we call a first article build, which can be very costly, because we have to get a small number of these enclosures and all the different components and start trying to fit them together and seeing where our process issues are going to be. But with this 3D model, this is really nice. This really helps us out. We can work together from this perspective, because I'm going to ask, kind of obviously right off the bat, how is that fan secured? Right. Seems like it's just sitting there. How are we supposed to secure that fan?
It's floating thanks to an anti-gravity field is what it's doing. See? No, originally the way I placed this was just to do the thermal sim. Mm-hmm. But ideally, I would want it assembled to the top. See, mm-hmm. I have a lot of little openings up here. Mm-hmm. So I would want it attached to this somehow, would be the plan.
Yeah, and what our engineering team is going to ask you is, well, how thick is that enclosure?
Tell you right now. I do a right click, edit feature. It's 2 millimeters.
Okay.
Using
2 millimeters, right? So typical fan, I think they use a 832 size screw, which, if I recall my rules here correctly, and our engineers are better at this than I am, that's probably around 3.5 to 4 millimeters of minimum thread connectivity. So we don't have enough space to thread in there and offer a viable connection. So this is where our typical design for manufacturability team would come in and give this feedback. We have two options, right? Depending on what you want to do here, we could run those screws down through the top, leaving like some pan heads exposed, and use nuts on the bottom of that fan and some thread locker to hold it in place, because we'll always use thread locker because vibration happens, even if you don't think it'll happen. But that's going to leave these kind of exposed threads. And one of the questions our team would have for you is, what is the look and feel you're going for here? Are you going for a real clean outside look? Do you want to minimize any possible user interference? If so, we'd want those screws to come up from the bottom of the fan into the enclosure itself. And so we would work with the enclosure manufacturer to add threaded inserts at those locations. They can either do press fit, or brazed on. We're looking at what's clearly a punched and folded metal enclosure, and that's the easiest way to add those threaded inserts. They add it during the punching process before they fold it, and then now we've got really good screw inserts there, and it should be really easy for us to assemble that. And thinking about that fan cable connected to that connector, this is again the kind of question we're going to ask you because we deal with this a lot. How long is that fan cable?
So that fan cable, if I look at the data sheet, if I remember, it's something like 300 millimeters long.
Yeah.
So a little bit over 10 inches.
So it's pretty long, because one of the things you definitely want to avoid, and this is one of the things that our team will be looking out for, as we talk about manufacturability, is we want to, if that fan is attached to that enclosure and then we have to put the PCB on there, we don't want to be in a fiddly situation where someone is trying to reach through and trying to plug in a little connector because they've only got 5 millimeters of space between the two to assemble it. So it's good that that cable is long enough, but it can create some other issues that our team would call out. We want to, the perfect world is someone can take this as a clamshell, connect it in, and then pop that PCB on top there like that, and then we're ready to go. So the cable's long enough to do that. It may be too long, and we'll talk about other strategies with you about, for example, we might zip strip that cable together to keep it from flopping around in there and keep it getting pinched. If we have real heat issues, our team would talk about how we add some attachment points to the enclosure itself to route that cable in a certain position. But those are the kind of things that we can do when we're sitting here working with the 3D model. Now, I did get asked a question here. Could we fix the heat sink to the TO220 at first and then solder them on the PCB as a whole? Well, the challenge is, remember, that heat sink is pulling heat out of that device. So it'll actually make it much more challenging. There's two problems we'll have with that. One is it'll make it much more challenging to solder it, and we're going to have to apply a lot more heat to the pins on that component to make sure that they solder effectively. And two, now we've got a big bulky device at what we call the plated through hole insertion. We go through a series of processes. We do SMT assembly, then the through hole devices are placed into location, and then we either go on to manual soldering or wave soldering or selective soldering, depending on the volume. That large heatsink is going to both make it hard to put that device into position and going to make it hard to solder it. So we would always prefer to do that as two separate activities. But yeah, so now I'm seeing, we're pretty close to having a manufacturable device. We've talked about how to test it. We found a few issues with the design, and we found a few, final assembly things that we can work out. And then There we go. So I think the question here is, what else can I help you with, George? Is there anything else I can dive into here, or do you want to go ahead and move into how you get this to how we work together to get this thing built?
So one final thing here,
Mhm,
as far as, because obviously this is a very long cable if it's 10 inches long.
mhm.
Is there cost differences versus, of having to zip tie it if you have to cut the cable shorter? Is it preferable to just be able to leave the full length as is and not, how's like what magnitude of cost differences are we talking about of just zip tying versus having to route it through the enclosure and all that?
Um, you know, it can be, if we think about, putting a fixture on there, right? Like say a little tie down point inside there, those can run a few cents each. Plus there's a handful of, there's some labor involved in doing that. Whereas if we were to use something like a zip strip, the total cost of doing that is typically a few cents. So the difference between that kind of clean cable routing or the zip stripping can run anywhere from about 50 cents to $1, depending on what we're looking for. So if you're really going for low cost, we can use zip strips. We could also potentially use something, like RTV or hot glue to secure that into position. It all just depends on where the cost is, what the look and feel is. There are always going to be a lot of options we have available to us.
Awesome. Excellent. So I want to go ahead and just show everyone the fully cooked version. We see the fan mounted to the top. I've adjusted the TO220s so that way they are always facing out. So you can see this one and this one, they're facing out. We have test points. These are the DC test points up here. And then we have the AC test points down here. So this is the revised design, taking all of Chris's feedback into account. Now, to our final topic, how do we get this to Chris, right? You have your awesome design. How do you get that information to Chris? So your manufacturing information, you have a few options. First off is the tried and true, right? We go here to the manufacturing tab and you click here on the CAM processor and you can just generate good old Gerbers. You generate the Gerbers, generate pick and place files, generate the drill file. Now, I know you guys take Gerbers, Chris, but is there any reason you would rather something else?
Yeah, so Gerbers are perfectly possible, and we get a lot of designs that are Gerbers and bill of materials, pick a place files. That does require a little bit more work on the user's part because sometimes these things don't line up perfectly with each other depending on how you export them, and we lose a little bit of knowledge about the design itself. What we have are sort of your traditional manufacturing outputs. So we have two options there. We can take the Eagle file directly, which is a very rich information source. We can process that. But we do have a lot of customers who are concerned about their IP. They don't want to send their entire design database to us. So with Eagle, you can export, or Fusion, you can export the ODB++, which is a very industry standard format. It does protect a lot of that IP. It's not a, you can't go and modify that design. It's just the manufacturing outputs. But with the ODB++, you can export that, you can upload to us, and we can extract your bill of materials, the part placement, the board design, everything from that one file. And with MacroFab, it is truly a drag and drop, right? You'll literally say, create new PCB, drag your ODB++ file in, and a few minutes later, you have a price and you're ready to go.
Excellent. So let me just quickly show ODB++ generation couldn't be simpler. If you want to set it up very specifically, you can use the CAM processor as I shown earlier. But if you click the ODB++ icon, it'll literally just generate all the files in one go. So I specify where I want them. Let's say desktop, just for, I hit save. It'll generate the TGZ file. And that's it. And it'll be right here.
And we take that TGZ file in just as it is with no changes.
That's right. Now, if for whatever reason you did want to export an Eagle file to send that to MacroFab, that's also possible. You can go here into the design, you go export, and you'll see under type, you have various options. You would pick the 9X board compatible files. okay? And you would send that to Chris.
Yeah.
And that's an option as well. One thing to keep in mind, very small caveat here. The polygon implementation in Fusion is much more efficient than the one in Eagle. So you don't have the trade-off of width to Gerber data size. So in Eagle, it would draw the polygons all lines in parallel, and the width of those lines would basically determine how many it would take to fill the poly. In Fusion, we're just defining the contour and then it fills. So you always have maximum resolution. So keep that in mind. If you do export the Eagle file, I do recommend just taking a quick look, making sure your polys are how you want them to be before you send them out. Because that is the one big difference in the output between Fusion 360 and Eagle.
And I see another question here. So I think Andy asks, what's the best way to capture panel tooling holes, whether it's Rabbit, VScore with MacroFab, and do we have any suggested templates? With the MacroFab platform, it actually automatically does the panelization. We prefer not to take panelized designs because the panelization changes depending on the lead time, which factories it may go to. We match the design, the order to a number of factories and a number of different vendors, and we optimize the price and lead time around that. So, by changing, for example, if you want to spend less money and go longer, we actually have a different panelization and tooling we would apply to that design than if you were trying to go faster and at a higher price. So we recommend just giving us your PCB design. The platform will automatically panelize it, and our engineering team will review that at order time to make sure there are no design impacts from the decision that the platform made.
Excellent. So less work for the customer, thanks to going with MacroFab.
Are there any layer limitations to Fusion 360? How many PCB layers do you guys
16
16
copper layers.
Okay, 16 copper layers. All right. And then one last question, I think here. Someone asks, how does Eagle now make a live bill of materials?
So Eagle or Fusion 360, neither of them right now makes a live bill of materials, something that's going. It is something we're working on though. So nice to see some validation from our customers. Currently, neither Eagle nor Fusion 360 make a live bill of materials, but that is going to be changing soon. So thanks for the heads up. Thanks for the comment.
Yeah. All right. So it looks like we're running low on questions. We want to go ahead and summarize what we've talked about today.
So let's go ahead and go back to our PowerPoint. We're just going to do a quick summary of what we've covered today. So first off, DRC, vital. When you're working on your board, one of the first things you should do is align your design rules to match your manufacturer specifications. That'll avoid false positives in your design, because the default DRC is very conservative. So if you don't match what your board house can do, you may get things reported as errors that your board house wouldn't have any issues with. And that just creates more work for you. So setting it up properly, make sure that you have as seamless a workflow between you and your manufacturing partner. As we were able to see, being able to have an accurate 3D model thanks to Fusion 360's E-CAD, M-CAD workflow really gives a lot of insight. If it wasn't for that 3D model, Chris probably wouldn't have seen that gap under the transformer and he wouldn't have asked about it. In this case, wouldn't have been an issue, but in others it would be. And you don't find out until that first product. Being able to have cloud data, I could share a link with Chris and Chris would be able to look at this without me having to give him full access to the hub. I could literally just give him a link, hey, let's check out the 3D model and see if there's anything you notice. And that's all possible because we have Fusion 360's cloud model. Keep in mind, not just the design. As an electronics engineer, you maybe stop thinking at, okay, I just generate my ODB++ or just generate my Gerbers and that's it. But you have to think beyond that. You have to think, how am I going to test this thing? How is this thing going to be assembled into the final product? Thanks to Chris, we went over manufacturing considerations, looking at cost, how easy it is to assemble, and repeatability. And as an engineer, when you have this conversation with your manufacturing partner, you can weigh off the trade-offs. You know, as we were talking, you know, zipping it versus actually having to weave it to the enclosure, depending on your product, you may favor one or the other, and it may not just be about cost. And then finally, we saw how ODB++ files can be super helpful because they bridge the gap between full IP reveal with Eagle files versus no IP reveal with Gerbers, and then giving a more usable data structure for manufacturing. Anything that I missed, Chris? Anything you want to add?
No, I think this is a good summary, and just as a reminder, at MacroFab, we will work with you, our team of experts. We've done this with many companies. We're producing a lot of products every day. We will work with you in each of these, and having the tool like Fusion to work together. You're not on your own, right? We'll help you, but having a tool like Fusion to be able to work together in will make that process much easier for us and faster.
Excellent. So if you want to learn more, here's the contact details for MacroFab. Definitely, as you can see, there's a lot of experience behind that team, and we're sure that they'll make your next project really seamless. So here's their details. Gonna leave them up for a second. And then here's Autodesk details. So this is worldwide. So anywhere in the world, if you need to get in contact, if you want to learn more about Fusion 360, if you need any type of help, these are all the numbers worldwide. So I'm going to leave them up for a little bit so that everybody can get a good look. And then, Chris, when you were looking at the questions, did you see the chat and the Q&A, or they were? Okay, cool.
I'm looking here. There's one last question. I think we probably have time, I think, to answer this.
Yeah, we do.
So the question was, with Fusion, what is the best approach to changing the board outline size and cascading this through the design?
Okay, so there's basically one key question here that defines what's the best approach. Are you using an off-the-shelf enclosure, and that enclosure is going to drive the PCB design? Or are you making a custom PCB and the enclosure is going to be based off of the PCB? Depending on the answer to that question, the best way changes. Looking at the more general case, more often than not, you're going to be using some standardized enclosure, which you have no control over, and the PCB needs to fit into it. In that scenario, the best way to proceed is going from the enclosure, you draw a sketch that'll be the PCB outline, and then you derive the 3D PCB from that sketch. That 3D PCB then gets linked to the 2D. At that point, changes in the upstream model flow down. So if something changes with the enclosure, now you had a switch and now you need to make room on the board, you go back to the enclosure model, you change the sketch. As soon as you save it, the 3D PCB sees that something changed, you update it, 2D PCB sees it, you update it. So if you have an enclosure that's standardized and that's what's going to be driving the design, then you do a derived PCB from there. If the reverse is true, then what you would do is you work on your 2D PCB, you then push to 3D, and then using that 3D model, you insert it into an assembly, and in that assembly, then you build the enclosure around it. Okay.
Excellent. Yeah. I think I understand. I've actually done that once myself in Fusion. I'm not the most expert Fusion user out there, but I did find, as long as I set it up correctly, it worked really well for me. So
excellent. Anything else? Any other questions?
No, looks like we've got it all.
Excellent. So we want to say thank you to everyone for taking this time to join us. We're really happy to have been able to share this information with you. The recording will be available and it will be posted to YouTube. So if there's nothing else, Chris, I really want to thank you for taking the time to go over this with me and for our customers.
George. Really enjoyed it. Always enjoy talking with you, and I enjoy being able to talk for an audience as well.
Excellent. So thank you, everyone. Have a great day.